Greetings YouTubers, my name is PhD Tony and today I'd like to present episode 1 in my Geodesy series, How Do We Know the Earth is Spheroidal? In this introductory video I will be describing a number of observational data sets that can be analysed to constrain the shape of Earth. In general, my focus will be on describing the observational techniques themselves and their relationship to the shape of the Earth, not on providing individual observations. Most people will not be familiar with the term geodesy, which refers to the branch of earth sciences dedicated to the study of the Earth's geometry, its rotation, and its gravitational field. Contrary to the expectations of flat earthers, geodesy is a mature scientific discipline with its own professional organisations, in particular the International Association of Geodesy and the Geodesy section of the American Geophysical Union. But let's move on to the topic of this video. How do we know that the Earth is not flat? Consider the case of an observer directly beneath the pole star Polaris. For this observer, Polaris has an elevation angle of 90 degrees. It is straight up. For every 111 kilometers southward the observer moves, the elevation angle of Polaris is observed to decrease by approximately 1 degree. Consequently, if the observer moves 2,500 kilometers southward, the elevation angle of Polaris will be observed to decrease by approximately 22.5 degrees, and if the observer moves 5,000 kilometers southwards, the elevation angle of Polaris will be observed to decrease by approximately 45 degrees. If we suppose the Earth to be flat, then these observations should allow us to calculate the height of the pole star using relatively simple trigonometric operations. But the results thus obtained by observers at different latitudes do not agree with one another. They produce inconsistent results. The height calculated for an observer at a latitude of 67.5 degrees is very different from the height calculated for an observer at 45 degrees. This inconsistency suggests that the underlying model we have used to perform these calculations is inaccurate. In other words, it suggests that the Earth is not flat. For an observer on a spheroidal Earth, however, the case is completely different. For such an observer, the elevation of a distant star above the North Pole is simply the observer's latitude. This result agrees very well with the observations available to us. While we have considered here the special case of the pole star Polaris, analogous results hold for the maximum elevation angle of any star crossing a given meridian of longitude. The apparent elevation of the star will vary with the latitude of the observer. One particular example is the Sun at noon. For some point in the tropics, the Sun will be directly overhead, but for observers north or south of that point, the elevation angle of the Sun will vary as an almost linear function of distance. In this diagram we have presented the particular case of an equinox, but the same observations can be made at any point during the year at any meridian of longitude. Again, these fundamental physical observations cannot be reconciled with the assumption that the Earth is flat, but they accord perfectly with what we would expect if the Earth were spheroidal. Our second observation is the shape of the shadow cast on the Moon during a lunar eclipse. Regardless of the season, regardless of the time of day, this shadow is always circular. The only possible shape for Earth that will always cast a circular shadow is a sphere. Further, our understanding of the relative motion of Earth, the Moon, and the Sun allows us to predict the occurrence of solar and lunar eclipses precisely, and to track where on Earth the shadow of a solar eclipse will traverse. These observations suggest that our understanding of the Sun-Moon-Earth system and its geometry and dimensions is accurate. Our third observation is the geometry of sunrises and sunsets. During these events, the Sun appears to be lower than the cloud cover, than hills, than the horizon. This is utterly inconsistent with the flat Earth geometry, but entirely expected as the Sun moves beyond the curvature of the Earth. The same principles apply to the observed patterns of motion of the Moon and the stars. Our fourth observation is the existence of two celestial poles of rotation, one in the northern hemisphere and one in the southern hemisphere. The existence of two such poles is entirely consistent with a spheroidal Earth rotating beneath relatively immobile stars. It is, however, entirely inconsistent with a flat stationary Earth beneath an allegedly rotating celestial vault. Our fifth observational dataset consists of images of Earth taken from high altitude or from Earth orbit. In these slides I am presenting images that were taken during the Gemini 5 mission, which occurred in August 1965. Flat Earthers routinely dismiss these images as computer-generated fakes. This conspiracy theory completely overlooks the relative dearth of computational facilities available in 1965, and also the general lack of expertise in computer graphics of this era. It also begs a significant number of follow-on questions. How many people are in this conspiracy? What is its budget? What is its motivation? Has there ever been anybody who has left the conspiracy? What are their recruiting procedures? Has anybody ever failed to be recruited? Just as a general rule of thumb, most reputable scientific curricula do not require that their students subscribe to the existence of a sinister, globe-spanning conspiracy with an unlimited budget and an infinite capacity for evil. Our sixth observational dataset comes from reciprocal trigonometric leveling. The inset here shows a 19th century design for an azimuthal telescope. This is a telescope that is designed to observe stars directly overhead. We established two such azimuthal telescopes at some distance from one another and use either laser leveling, water leveling, or plumb bobs to make sure that they point directly upward from Earth's surface. We then use precise observational techniques to measure the angle between the upward line and the line of sight towards the corresponding point on the other instrument. We do this for both instruments simultaneously, and we obtain measures of the internal angles subtended at each instrument. If the Earth were flat, then the upward rays from each azimuthal telescope would be parallel. Therefore, the angles θ1 and θ2 observed at each of the instruments would be supplementary angles and would add up to exactly 180 degrees. In practice, we observed that the angles subtended at the two instruments always add up to more than 180 degrees. This requires that the upward rays originating from each instrument diverge, which in turn is entirely consistent with both instruments sitting on the surface of a spheroidal Earth. Our seventh observational dataset again comes from the field of surveying. In this case, we look at any three widely separated points on Earth's surface. These points define a triangle. Now, if the Earth were flat, this would be a planar triangle and the internal angles would add up to exactly 180 degrees. But in practice, we observed that for any three widely separated points, the angles always add up to more than 180 degrees, which is entirely consistent with the spheroidal geometry. For our eighth observational dataset, we consider simple geometry. Consider 2 points on Earth's surface. We can determine the latitude and the longitude of those points by celestial observation. That is, by observing the relative position of stars of known declination and hour angle. Once we have determined the position of our 2 points, we can then use spherical trigonometry to calculate the angle distance between them using the spherical cosine rule as described here. We can then estimate the distance between the 2 points by multiplying the angular distance in radians by the radius of the Earth. For any arbitrary pair of points on Earth's surface, the distance estimate obtained by using this technique is always very accurate. In stark contrast, flat earthers have no technique for accurately estimating the distance between 2 points on Earth's surface based only on their latitudes and longitudes. Our ninth observational dataset consists of the simple act of navigation. Navigation works on a spheroidal Earth, it does not work on a flat Earth. I present here the simple case of Entebbe International Airport and Supadio International Airport in Indonesia. These two airports lie very close to the equator. Therefore, on the spheroidal Earth, all one needs to do is head east and fly in a straight line. On a flat Earth, one takes a bearing 52 degrees east of north and then flies in a straight line. You can certainly attempt this on the real Earth, but you will not end up anywhere near Indonesia. Every day, tens of thousands of marine vessels and aircraft arrive safely at their destination. They have relied on spheroidal geometry to get them there. Each and every safe arrival is observational validation of the spheroidal Earth. Celestial positioning and spheroidal navigation have been used successfully for hundreds of years to navigate across Earth's surface. One of the most triumphant applications of this technique was the journey of Captain William Bligh after being set adrift by mutineers. In a tiny vessel and with minimal equipment, Bligh was able to navigate more than 6,000 kilometres to safety, demonstrating yet again that spheroidal navigation works. Our 10th observational dataset comes from the field of seismology. On Christmas Eve 2004, a magnitude 8.1 earthquake occurred at the Macquarie Rise, which is marked on this map by a red star. The seismic energy released by this event spread out from the epicenter and was recorded at a number of seismic stations around this region. The locations of the seismic stations are indicated by red circles. The more intense the red, the closer the seismic station is to the epicenter of the event. The blue circle marks the location of the most recent station to register the event. The epoch considered in this slide corresponds to the time slice between 11 and 12 minutes after the event occurred. The panel on the left shows an azimuthal equidistant projection focused on the epicenter of the event. Under this projection, we can see that the energy from this event is radiating away from the epicenter in a roughly circular pattern. We can also see that the energy has travelled from one side of Antarctica to the other side of Antarctica in a relatively short period of time. The panel on the right shows an azimuthal equidistant projection focused on the North Pole, the preferred projection of flat earthers. Under this projection, the energy from this event has travelled from one side of Earth to the exact opposite side of Earth very quickly without passing through any of the intermediate portions of the Earth. This dispersal of seismic energy is weird and inconsistent with any physical model currently available. In stark contrast to the bizarre non-physical behaviour of flat Earth models, spherical models allow us to predict what seismic phases exist and when they will arrive at a particular seismic station. These arrival time predictions have been compared against observations and found to be extremely accurate. One particularly interesting form of seismic energy takes the form of surface waves, in particular Rayleigh waves, which are observed to travel around the world multiple times. Here we show a seismogram obtained from the Marble Bar seismic station for the Sumatra earthquake of 2004. A small schematic of the relative position of the event's epicenter and the seismic station are presented in the inset. Rayleigh waves radiate in all directions away from the epicenter of the event. In particular, they radiate along the great circle connecting the seismic station and the epicenter. There is then a Rayleigh wave radiating towards the seismic station along this great circle and another Rayleigh wave heading in exactly the opposite direction. The arrival times for the first Rayleigh wave are marked with yellow arrows and for the second in red. The second Rayleigh wave has to travel around the far side of the Earth in order to get to the seismic station and thus arrives considerably later, but then continues on its way and comes back again having completed a second lap of the Earth. There is simply no way to reconcile these observations with a flat Earth geometry. Okay, so that brings us to the end of today's episode, and I apologize for the length of the video. It kind of got away from me there. But what I hope I've done is presented a series of reasonably comprehensible observational data sets that demonstrate the shape of the Earth. Realistically, of course, there are many hundreds of other data sets that will do the same thing, but we'll leave those for another day. Anyway, thank you everyone for watching.